Okay, guys, so last time we went over chemical bonding. We started with talking about how the elements, before they actually bond, how they want to have a full outer shell of electrons. And then we finished up with talking about covalent bonding and how when two elements are bonded together with a covalent bond, they're sharing those electrons. So we're going to start off today talking about the opposite type of bonding, which is ionic bonding. Instead of the elements sharing electrons like in covalent bonding, instead here they're going to gain or lose an electron. Okay, so if we look at these two here, and let me stop this animation from going. If we look at these two here, this is sodium, Na, and this is fluorine, which is F. So I already drew they drew the diagrams for you, but you could see that sodium has one electron in its outer shell. Now we talked about them wanting to have a full outer shell of electrons, okay? Well, sodium could do one of two things. And the first thing it could do is it could gain, it wants to be full, right? It wants to have 8. It could gain 7. That's a lot to gain, okay? But what it could also do is just lose that 1. And then, if it gets rid of that 1, guys, okay, so if I have it here where this 1 is gone, so it's no longer there, that means this whole outer shell no longer exists. So the whole thing's gone, okay? If that happens, then if I change my color up here, that makes this red shell, I'm making red here, this shell is now the outer shell. Okay, so if we count our electrons in that shell now, it has 8. So even though it's going to lose this 1 that I drew on here, the shell below it has 8, so it's happy. Okay, now fluorine over here on the other side, with the F, it has 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. Those are called valence electrons, electrons in its outer shell. So it wants to gain 1. So these two are like a match made in heaven. The sodium wants to lose 1. The fluorine wants to gain 1. So what happens here is that electron gets lost and it goes over to our fluorine there. Okay. So it comes over and now fluorine has 8 as well. Okay. So yeah, sure. Okay. Sodium loses 1. Fluorine gains 1. Sounds good, but where's the bond come, right? So the bond, guys, is in this, I guess we can say swap, in sodium giving fluorine the electron, fluorine becomes bonded to sodium, okay? All right. So that's an ionic bond, a little bit different than a covalent bond, okay? Again, this one is gaining and losing electrons, whereas covalent is sharing electrons. Okay, so we're going to go back. Your book explores the states of matter one more time. You guys know all atoms are in constant motion. We already talked about the solids. They vibrate in place, okay? If we were back in school now, you could look at your desk and I would say, hey guys, is your desk moving? And you would say, well, you're telling me it is, right? By these, well, the desk is not moving, guys. The desk is stationary. But the molecules, all those atoms that make up your desk, they are moving. Okay, they're vibrating in place. But your desk, it has a fixed volume and a fixed shape. Liquids. We talked about liquids at the beginning of this chapter. Liquids have a fixed volume, okay? We know that, like, if you get a pop or something like that, it's 20 ounces. That's a volume, okay? You have 20 ounces of pop, or a 2 liter of pop, okay? But we could change the shape depending on what container we put it in, all right? So that is liquids. And then lastly, we have gases. There's no shape, no volume, no rhyme, no reason to these gases. They just fill whatever they are put in, okay? If you fill your room with gas, air fills up the whole room, okay? For us, our biggest container we have is planet Earth. We have the ozone layer that keeps all of our gases in, all right? Okay. Next thing here, guys, we are going to go over chemical reactions. All right, so right here, down at the bottom, we have a chemical reaction. And that is a chemical reaction between hydrogen H, and oxygen, O. Now, we're not going to worry about why the 2's are there between hydrogen and oxygen, okay? You'll go over that in chemistry, but here's what I do need you guys to know, okay? On this side, we have the arrow here, okay? These are called our reactants. This is what we put into a chemical reaction, okay? Again, they're on that side of our arrow, all right? So those are our reactants. And then, just like in math, like if you do a multiplication problem, you get a product out of it. What we get out of our chemical reaction, these are the products. And here we only have one product, and that is water, okay? But sometimes we can get more than one product, all right? So what I need you guys to know is reactants are on left side of the arrow. Products are on the right side of the arrow. All right, your metabolism, guys. We talked about this in chapter 1. This is a sum of all your chemical reactions in your body. And your body is constantly, always using energy and releasing energy. So your body needs a constant supply of energy. If that changes at all, you're in trouble. If you don't have energy, your cells are not going to have energy and they're going to die, all right? So let's talk about the energy that we need. And we're going to talk about a really small process in your body. We're going to go like to the molecular level. So with all this, guys, we are going to have something that we need called an activation energy. That is the energy, and make sure you know this definition, that is the energy needed to start a reaction. Okay, that's your activation energy. Energy needed to start a reaction. So it's kind of an all or nothing thing. So picture this guy going up the hill, and the charts, the graphs that we're going to do look exactly like this. If this person is trying to push this rock up the hill, okay, let's say that they don't get it all the way up the hill. Let's say they get the rock to here. If they only get the rock to here, it is not going to go up and over. That's not going to happen, okay? So, like I said, it's an all or nothing thing. The rock is going to have to go to right here, and once that person gets the rock to there, then that rock can fall down the hill, roll down because of gravity, all right? But again, guys, if you don't get it up the hill, the rock never goes down, okay? I thought this picture was funny. It reminded me of activation energy because that's what's going to happen on the other side. If there's people on the other side and you roll that rock down the hill, thank goodness the ball is like nice and squishy. But never mind. There's a rock coming. Oh my goodness, that poor guy. I'm so sorry, guys. I didn't know there was going to be death today. Okay, I'm done. I'm sorry. I couldn't help myself. So reactants and products. Here's what we're going to have. So here's your activation energy graphs. This is what they are going to look like. Okay. So again, this is your activation energy graph. And they're all going to look like this. Okay. You're going to have something starting. It's going to go up a hill, and then it's going to go down a hill. The hill that it goes down might be big, it might be small, whatever. On this side of the hill are going to be our reactants. On this side are going to be our products. So just like if we go to this previous slide, right here, we had our reactants and we had our products. That arrow represents the hill, okay? If we do not have that ball, I guess we can call it, go all the way up the hill, we're not going to get any water out of our hydrogen or oxygen. So we need that arrow to be the whole hill, okay? If not, we don't form any water. Okay. So I'm going to go back to here. Here's how we are going to estimate our activation energy, okay? So I'm going to draw a line to the best of my ability, coming straight over from our reactants, okay? And I don't know what number this is. You guys know on a graph this would be 0 here, okay? We'll call this, I don't know, we'll say this is like 5. We'll say this is 10. All right, 15, 20, 25. We'll call that all the way up there like, oops, we'll call that like 30. Okay, good enough. So the size of our heel from here to here, that right there is our activation energy, okay? And we can calculate activation energy. So if we wanted to calculate that, all right, you could see that probably around 30, that's around the top of the hill for estimating, somewhere around there, okay? The activation energy is not going to be 30. It's the size of the hill. The hill starts at 10. So our activation energy is going to be 30 minus 10, and we get 20 out of it, okay? That's how you calculate activation energy. And here's another example here, guys, of activation energy, okay? Only thing I need you to know is activation energy is the size of the hill, reactants are on the left, products are on the right, and we need to get up over that hill, okay? So here is 2 different reactions, okay? They both have the same starting point. In other words, if we were to look at where the hill it starts at, it's right here, and we just carry that line all the way over. I'm not going to draw across there because there's no way I'm drawing a nice straight line for you guys, but you can see that the reactants are going to start off at the same energy. Now, the hill is much taller on this one compared to this one. Think about you guys. Think about the person trying to push that rock up the hill. If it's a bigger hill, then, well, it's going to take a lot more energy to push that rock up. So if you look here, okay, our activation energy, I'm just going to do it in non-numerical terms. Our activation energy is going to be big. This requires a lot of activation energy to push that rock up the hill. This one over here, okay, is nice and small. So we don't require a lot of activation energy on that side to push that up the hill, which is really nice, you know. So which one do we want for our bodies? Do you want your body to be like the first reaction here, where it requires a lot of energy to do all your body's processes? No, you don't. You want the small one on this side because we want to save our energy. If it requires less energy for our body to do whatever it needs to do, we get more energy to do other things. You guys can go and, like, you know, play sports or whatever, okay? So there's your difference between the two. Okay, we're going to talk about catalysts, things like enzymes. And we're going to talk about what enzymes do for you. So again, we have these 2 reactions here, right? Catalysts reduce the amount of activation energy required. So if you look here, we're talking about reducing. Which one would have the catalyst in it? Well, number 1 is very big. Number 2 is very small. So number two would have the catalyst, okay? So this one on number 2, the catalyst or the enzyme is present, okay? Is present in that one. And it's absent in the opposite. All right? Here's another example, guys. You can see the red one has a bigger hill than the green one, okay? The smaller the hill, that means there's probably an enzyme present, okay? All right, last thing for today, guys. We're going to have 2 different types of reactions. We're going to have exothermic and endothermic reactions. Exothermic gives off heat, and endothermic requires heat, okay? Exo is like, it means out, okay? So the prefix exo means out or outer. Exothermic, they give off energy. Endothermic, they absorb energy, or they need energy, okay? Look at the difference between the graphs. In exothermic, okay, if we were to draw a line between our reactants and our products Do you guys see how it goes downhill like that? That is exothermic. So our reactants are higher than our products. The opposite way, so downhill was exo. The opposite way, if you look at this one, our reactants going to our products is going to go upward. Okay, that's endo. Or we could say our reactants are below our products. So that's an endothermic. So that's how to tell a difference. Just draw a line in between the two. If it goes up, it's endo. If it goes down, so if the products were down here, it would be exothermic. All right. Okay, guys. Tomorrow, we'll review a little bit more with activation energy, and then we will start on enzymes. Have a good day, guys.